Good morning, everybody. We get started now. Welcome to the the fifth edition of the Quantum Engineering Workshop. I'm Marco Quadrelli. I'm organizing the workshop with Professor Husnud from Cal Poly Pomona. And this workshop is sponsored by Cal Poly Pomona, ASME, American Society of Mechanical Engineering, Caltech CAST. And we are very happy that we are continuing for a fifth year here. So let's see. The vision of the workshop is to, let me give you some background here. We're trying to integrate quantum technologies with quantum engineering systems to enable novel opportunities in space exploration, terrestrial science, and engineering. And so we aim to bring together engineering and physics experts together in from multiple areas of the respective fields and exploring the interface. The main goal is to learn to use the same language, because we have observed over the years that there are a lot of people with a strong physics background that are working on quantum technologies and doing applied physics, but the engineers do not, when they try to bridge the gap and start to work in together with their colleagues, that there's some language barrier there. So the objective is to develop a community of practice, which we have seen over the years that has been developing and is growing, I wouldn't say exponentially, but very quickly. Initiate joint research collaborations and infuse quantum engineering curriculum into the educational curriculum of the engineering disciplines as well. This year is a particularly interesting year because it also has been designated, proclaimed by the United Nations, the International Year of Quantum Science and Technology. Because it recognizes 100 years of the development of quantum mechanics. So this is, there's a link there. I'm sure most of you already know about it, but there's multiple ways to engage. And this is another opportunity to expand the community and collaborate. So I would like to say we did the same last year as well, kind of put things in context, because putting things in context kind of gives the motivation and gives also the impetus to maybe ask the right questions, I hope. So if we kind of divide, I don't know, the landscape, let's call it landscape, between with attributes like you see here, classical systems on one end, quantum systems on another, quantum regime and classical regime. And I'm sure that some of the people here, the professors that are teaching these every day, they may have different opinion, but this is just our neck of the woods vision, and maybe we can foster some conversation. I have worked for many years in my career at JPL on spacecraft and many different types of missions. So I would consider those classical systems operating in the classical regime, although of course there are many exceptions, and you can see some of them up there. For example, the optical atomic clock and so on. But these are all the ones that are in flight. And so there's many of them. On the other hand, approaching the...
We've lost the audio.
You lost the audio? Where's the audio?
Okay, we got it back.
Is it back?
Yeah, it is back now.
Okay, thank you. Yeah, so going now into the staying in the classical regime, but starting to infuse more of the physics at the quantum level, then now there are some of these missions that have to do with gradiometry, gravitational waves, and so now the phenomena at much smaller scale, they require a different type of approach. So now that's why we put them on that end. On the other hand, there's quite a bit of work being done on quantum computing and instruments on the space station, for example, they're called atom interferometer, the Bose-Einstein condensate also back up, and a lot of these type of conversations occur in a domain where the quantum systems are pretty much in the quantum regime. So if you don't speak the language of the people that are working in those projects with the right approach, then you're lost. Finally, there is another area here where, because Farbod and I are spending many years doing robotics, there's an area where macroscopic systems, so classical systems, can be interfaced with quantum techniques or quantum protocols, for lack of a better word. And so we call this area quantum robotics. And we also have a wiki page, and I'll have a link for that later. So this is one snapshot of the situation. So what do we mean by quantum engineering? Well, it's this emerging field of physical engineering, which is based on hybrid classical and quantum properties and their utilization for practical applications to deliver useful devices and processes based on quantum principles, which, however, have no classical analog. And you know what they are: superposition, entanglement, and so on and so forth. And there's if you try, and I spent a very long time scouting in the literature, try to find some kind of a unified perspective of where things are going, where things are. And so I've seen four main areas here. So there's an area which is within quantum engineering. There's quantum computing and simulation, where people are talking about digital and analog quantum computers, quantum system simulation, quantum circuits for simulation, quantum optimization techniques. Another area is quantum communication and cryptography, where now, for example, and there has been already demonstrated, what you see here, the 144-kilometer free space link between the Canary Islands and La Palma and Tenerife, and with a classical channel and a quantum channel. So this goes through space, basically. And then there's the area of quantum sensing and metrology, which is probably the most mature area. Area now, the devices, the detectors, the single photon count devices, things like that, timing, clocks, techniques for quantum imaging, and also quantum radar, which is kind of an ambiguous domain, because some people say, yeah, there's nothing there. Some people say, oh, yeah, we can do quantum radar. And then there's the area of quantum materials and chemistry, where now there's a lot of, and many of the talks today, including the next one, they're into nanosystems. Oops, my God. Oh, thank you. Yeah. And so now we're talking about spintronics, topological insulators, computational techniques for chemistry, and so on and so forth. So this landscape is very wide, and I would like to also mention this, because this is a chart that people use when they do technology forecasting and assess the maturity of emerging technologies. This Gartner Hype Cycle, for example, where which shows this hump at the beginning of where everybody's enthusiastic about it. We can do everything with this technology. And then there's a hump on the other, there's a well there where people get disillusioned, and then there's a plateau at the end, all after some time. So and we can start a conversation today, and I hope that you don't throw tomatoes now at this point, but many people agree that quantum computing is still in the hump. Quantum communication is more mature because it has also has been already demonstrated to some extent. And quantum sensing is most definitely the most mature of all the techniques. I would say then, talking still about context, I mentioned the macroscopic scale, all these missions, these spacecraft, where now quantum principles are not necessarily important at the mission scale. And so this is a case where we are acting, and we've been very successful at it for decades, act classically in classical systems. We do that very well. We do that every day. Then we also have people acting quantum mechanically on quantum systems, and these are some of the examples where now the micro to macroscopic scales are the mesoscopic scale are more important rather than macroscopic scales. Quantum system performance at the quantum level is critical, and understanding insight at those scales are extremely critical. And we're now, the quantum principles are extremely important at the mission scale. The mission scale could just be operate this quantum computer right there. Finally, there is the other area, which is act quantum mechanically on classical systems. And you could say, yeah, well, in the limit, Ehrenfest theorem allows you to do that. But this is a little bit different because we are trying to bridge. Thank you. We're trying to bridge the small and the big in a hybrid manner. And so this is a new area. Again, the landscape is very wide. And over the last 5 years of the workshop, we have been very fortunate to have speakers and met a lot of distinguished speakers and made friends with many of the people operating in most of these areas. And from again, sensing, quantum control, simulation, materials, biophysics, quantum cognition, where now psychologists bridge with quantum. That's another area, emerging area. And I'm sure there's many others. I didn't capture all of them, but the bottom line is that we have been covering this ecosystem pretty extensively, and we hope to do so as we go forward again, because it will continue growing. And if we don't have a structure, if we don't have the context, if we don't speak the same language, if you're not in a position to speak the same language, we interact with people in this ecosystem, then I think we are in trouble. It's going to take a long time to get to practicality. I would say that there are many. So the national academies, they have been, of course, monitoring the progress in many areas. I spent my career in working in, for example, air science, planetary science, astrophysics. So this is what I'm more familiar with because of my professional bias. But there are these reports give you the state of the art. These are, you can download them from the website. You can find what the state of the art is and what the projection is for the next 10 years or farther out, or what the science community perceives that is important at the national level. And so, for example, this is the latest planetary science decadal survey. And for the first time in the planetary decadal survey, there's a lot of mention of the word quantum computing, quantum sensors, and this is, to me, symptomatic of the times, which tells us that is the right time to start bridging that gap more effectively. This is the astrophysics one, where again there's mention of for application of quantum computing, quantum information for quantum sensing in various frequency bands of relevance for astrophysics, and for air science as well, where we already have people working and developing quantum gravity cardiometer. One of the speakers this afternoon will cover that. So I'd like to mention, and then there's, for example, the Thriving in Space. This is the biological and physical science decadal survey, where, of course, there's quite a bit of gravitational sensing, quantum optical detectors mentioned as recommendations, that things that need to be developed. The quantum computing one says that, concluded that in 2019, that there's no fundamental reason why a large fault-tolerant quantum computer could not be built in principle, but that there are many challenges. I find this report particularly enlightening, and I've referred to it many times in the last few years. And all of them kind of, there's consensus that there's three things here. One is that we need to be cautious, and I remind you of that Gardner curve. that we can talk, oh yeah, with quantum technology, you can do everything. And we need to be very cautious, because one thing is quantum advantage, which refers to a case where a quantum computer, for example, quantum computer is able to solve real world problems that a classical cannot. Quantum practicality is similar to that, but now there's the issue of performance. The computer can do things faster. And quantum supremacy is that we not only can do it faster, better, but it's very likely that the problems being tackled they're just theoretical or mathematical exercises, or very abstract and not exactly practical, at least at this time. I would like, because I spent my career in the robotics, autonomy, guidance, navigation, and control area, and working on all those systems that I mentioned before, through looking at what people have been doing in quantum technologies. I would say that, and just as a reminder, guidance. I'm sorry.
Yeah, bon.
Please mute yourself.
Can you mute yourself? Yeah, I think we're okay. Yeah. So there are a few areas here where quantum technology is really very mature, and in order to claim that we can use quantum engineering, be quantum sensing or quantum computing in areas of interest that involve guidance, navigation, and control, there are things that need to be developed. For example, yes, we do need modeling simulation. We need to be able to preserve state coherence, entanglements, timing and synchronization. When we do the measurements, we need to have actuation techniques that probably involve automechanical solutions, which have to be fine-tuned very carefully. Instrumentation is very related to quantum sensing, but some people are starting to work in bridging, for example, inertial measurement units with other types of quantum specific detectors in order to increase performance. Quantum control is very mature from the quantum state feedback, and one of the speakers this afternoon is a distinguished speaker in this area, distinguished researcher. Task scheduling, hazard avoidance. Some people have already been working on this, but there needs to be more mature development in quantum parallelism and quantum random generation and machine learning, and most importantly, particularly for systems like space systems, where human intervention has to be very limited, especially for planetary ignition, and so interventions are very rare. Systems engineering with verification and validation in the quantum regime is still to be developed, so it has not been done yet. So, okay. Yeah. It's not advancing. Okay. So, yeah, so I would like to, before for Bob introduces the rest, and maybe you want to talk about this, because this is more in your domain, because you're a professor. You're an educator. So there's the education aspect.
Yes.
The creating a curriculum that is effective in bridging quantum technologies with traditional engineering disciplines. And Bob has already experimented with it, and many others around the country. And in the course of the 5 years of our workshop, we've seen that also other speakers have reported that they have had success. For example, in their electrical engineering classes, introducing quantum physics and the areas of quantum networking, quantum sensors, quantum computing, quantum algorithms as part of the curriculum. So we think that, and we have also written some papers together with some proposals on how to do this. We think that this is very critical because the workforce of the next few years is going to need this type of capability. So we need to prepare the students to that. So I'll pass the ball to you. Yeah.
At the same time, also, just to add that, so we know that there's a lot of great work is going to in the areas of computing, quantum computers, and so on, and physics, of course. But we really lack the quantum knowledge in the other programs like mechanical engineering, aerospace engineering, aerospace, and electromechanical, let's say. So therefore, this is what we are trying to do. For the first time, we incorporated quantum by also the way that we do it. We start with the experiments, explaining the experiments rather than explaining the theory. And then from the experiments, then we go towards how to explain all these different phenomena in the quantum, including entanglement, quantum cryptography. So I think by nature, for engineers, it would be more practical to start with the experiments and explaining how it works, the system, and then go to the theory. So that's how we do it. And even though the students don't have any background, undergraduate student with no background in quantum physics, absolutely nothing in the past, no exposure, but they can follow, understand how the experiment works, and then from the experiment, then they can learn the theory later on. A little bit of theory, especially we do on the quantum entanglement, as well as quantum key distribution and quantum cryptography. That's the main purpose for us at the moment for the teaching, but we can also add that. So we have also organized these workshops. Well, this is the 5th year. We have many distinguished speakers in the past, and we had the honor of inviting many speakers. And this year, we have also we have the honor of having many distinguished speakers again. So our first speaker is Professor Michael Ruckus, who is the Frank Roshek Professor of Physics. Okay, so this is the program. And so just to let you know that the morning we will be here in this, Professor Ruckus will be presenting, and then Professor Paulsberg. And then we have a short break, as you see in the program. Then we have 2 online speakers, and then we have a short tour of the Center for Autonomous Systems and Technology. We demonstrate our quantum robotics, which is really robots with multi-agent robots with quantum communication. And then we have the afternoon event in different locations, which are sent to everyone, but the same Zoom link. There is a little bit of change in the schedule in the afternoon. So the 5 p.m. Talk will be during the break because the speaker, Dr. Nicole, is not available at 5 p.m. So she will be speaking at 3 p.m. during the break time. And so I think that's all for the program. Our first speaker in the afternoon will be in person, and most of the rest of the afternoon will be also remotely. So if you like to join remotely, if you're in person and like to join remotely later on, you're welcome to do that, however you prefer. The location is different. We can walk for the CAST tour, we walk from here. So we have to leave exactly 12 o'clock because there's a class going on right after this event at 12. So we walk almost next door to the CAST and quick demonstration about 10-15 minutes, and then you're free to, and then you can come back at 1:30 to the next location.